Welcome to this section on breast cancer detection. Our task here is to make use of this microscope images of breast tumor cells to predict whether a given image is a benign cell or a malignant cell. It's fine if you don't understand exactly what a benign or a malignant cell means, but just note that a benign cell is one which is considered non-cancerous, while a malignant cell is considered to be a cancerous cell. And also in this section or throughout this section, you would be getting to work with this medical data, which normally only people from the medical domain should master. But note that for experimental purposes like this, you may not need to understand exactly everything about the kind of data you're working with. Although if you are to release a product like this for real life usage, then it's very important that you work with someone from this domain so that you can take advantage of their expertise to bring out the best of the models you shall be building. That said, let's go to this link and get our data set. This breast cancer histopathological database, that is the BREC-HIS, is composed of 9,109 microscopic images of breast tumor tissue collected from 82 patients using different magnifying factors, that is 4 times 40 times 100 times 200 and times 400. And to date it contains 2,480 benign and 5,429 malignant samples. So we'll see already that this data set is imbalanced, since as we have more malignant samples as compared to the benign samples. These images are several hundred by 460 pixel with 3-channel RGB and 8-bit depth in each channel. They are also in the PNG format. This database has been built in collaboration with the PNG Laboratory, Pathological Anatomy and Cytopathology in Paraná, Brazil. Let's now look at some characteristics of this data set. The BREC-HIS data set is divided into two main groups, as we've seen already, the benign tumors and the malignant tumors. Histologically, benign is a term referring to a lesion that does not match any criteria of malignancy, that is marked cellular atypia, mitosis, disruption of basement membranes, metastases, etc. So what we can note from this phrase is that a benign cell is one that does not match any criteria of malignancy. Now, normally benign tumors are relatively innocent and present slow growing and remain localized, while malignant tumors are synonymous to cancer. The lesion can invade and destroy adjacent structures and spread to distant sites to cause death. In the current version, the samples present in the dataset were collected by the SOB method, also named partial mastectomy or excisional biopsy. This type of procedure, compared to any methods of needle biopsy, removes the largest size of the tissue sample and is done in a hospital with general anesthetic. In this table here, we see exactly how many benign cells were gotten with a times 40 magnification, how many times 100, how many times 200, and how many at times 400. So again, if you have to design a model or come up with a solution which is to be used in real life, it's important to work with a medical practitioner, as they'll understand all these terms we've made mention of so far. Now, both the breast tumor, benign and malignant, can be sorted into different types based on the way the tumoral cells look under the microscope. Various types or subtypes of breast tumors can have different prognosis and treatment implications. The dataset currently contains 4 histological distinct types of benign breast tumors: adenosis, fibroadenoma, phyllodes tumor, and tubular adenoma, and 4 malignant tumors, that's the carcinoma, lobular carcinoma, mucinous carcinoma, and papillary carcinoma. And the way the file names are stored depends on these subtypes. Like if we have a file name like this, we could break this down into SOB, that's a method which was used, that was set here to collect the data set. Then B for benign, TA for tubular adenoma. Then the 14:4649 is a code we get the authors of the data set got from the slides. 40 meaning that it's gotten at times 40, and 001 is an image number 1. Here are examples of malignant cells seen under different magnification factors. A is 40 times, this times 100, times 200, and then times 400. This data set was published in the paper by Hall, Oliveira, Petitjean, and Hurt L. entitled "A Data Set for Breast Cancer Histopathological Image Classification." So to access this data set, you could simply fill out this form right here. And here are some other 2 papers where this data set was used. Now, what's also very interesting to note about deep learning techniques is that without having necessarily to be an expert in this domain, you can actually build upon the data set, or build using this data set a model which does quite well in predicting whether an input image is benign or malignant. But as we've said, and we repeat again, if you have to come up with this kind of model in a production setup, it's very advisable to work with a domain expert. We now go ahead to import all necessary packages. Our byte size is initialized to 32, input dimension for the images 224, number of epochs say 20. Then we specify the training directory. We use TensorFlow's pre-processing the image data set from directory model, which makes use of the organization of the files in the train directory to create a TensorFlow dataset. After downloading the dataset, we shall have these 2 main folders, the benign images and the malignant images. For the benign, we have the method which was used to get the images, that's SOB method. Then the different subtypes. For the adenosis, for example, we have this. You see here we have the type, we have the fact that it's benign adenosis, the code, and then getting into this, we have the different images based on the magnification. So like this gives times 40, times 100, times 200, times 400. So opening this, there we go. Could go and see some other images in this times 400 magnification. Let's close this, then get back. Look at this other one, see the images and things like that. Now, as you may have noticed, we have these 2 folders, and then the benigns could be considered to belong to the class 0, and then the malignants considered to be of class 1. So this means that when creating our data set, we want that an image coming from this benign folder would have an output of 0, and an image coming from this malignant folder would have an output of 1. But then TensorFlow makes it very easy to work with such data sets where we have different classes, which maybe even greater than 2 classes, be in different folders. So if we had another class, say, let's say another class. So in this case, if we have 3 classes, and then we put images in this, images in this, and images in this, the way TensorFlow does this is using this image data set from directory, we could automatically create inputs and then give them an output depending on which of the folders they belong to. Now note that once we stop at this position here, this breast, after this we have either the benign folder or the malignant folder. So what TensorFlow does is it gets into the benign, all the images in the benign, whether in subfolders or not, are considered to be of class 0, and then in the malignant, all the subfolders and images, or all the images in the subfolders, are considered to be of class 1. And this is done pretty easily with this function. So this function now takes in this directory which we've defined already. There's a validation split. In our case, we suppose our validation set is 0.1 of the total data set, and then the subset we're working with, or we're trying to create here, is a training. So we specify the subset to be training. The seed is fixed so that the way the random shuffling is done doesn't change when we get to create the validation set here, because if we have a seed which isn't fixed, then after shuffling here we shall again shuffle our data set here, which is not what we want. Now once we have that, we also specify the image size. So if the images have a size, say 768 by 496, now they have this new shape, which in this case is 224 by 224. The channel size is not included. Then we have the batch size, which is given. We've specified that already. So from this, we now run this and run that. We'll see from here, we have 7,909 files belonging to 3 classes, and then 719 files for training, again 7,909 belonging to 3 classes, and then 719 for validation. So this extra class we added, we just take it off, and that's it. We now come back again to run it. We see that now we have TensorFlow recognizes 2 classes. Again, we have this number of files for validation, number of files for training. We could also get some information from this data set which has been created, the train data set, the different class names. We could look at how what the train data set looks like, and then we could go ahead to visualize some of the images in the data set. So there we go. Specify the figure size for the image and labels in our train data set. We take just one batch. So now we have a batch size of 32. So we'll take 32 images then. Then for these images, we simply plot each and every one of them as a subplot, where we have this 15 subplot positions since it's a 3 by 5 array. We could obviously have 32 since our batch size. We'll just say batch size, and then here we have batch size divided by 4, that's 8, and then batch size divided by 8, that's 4, so 4 by 8. Now we have that. We also add the class name every time we show the image, or we plot the image. We run that, and there we go. We have this 32 different images. Then we implement caching and prefetching. So from this, let's see what our training data set and validation set shape look like. Training data set and validation data set.